So after being comfortable with calculating with radians, converted between degree and radian and so on, we move on to replacing most of the formulas we know with, instead of degrees, we use radians now. And actually this is where using radians becomes much more comfortable. So just to recall, these are the parts of a circle. This was taken from online mathlearning.com. So we have a sector, which we're going to use here. So a sector is a part of the circle that's created from two radii. So this is your radius and an arc. So it's the area enclosed between them, between those three. And a segment is the area between the arc and a chord here. So we will be dealing with sector mostly and the arc length. So the arc length could be here, or as part of the segment, and we'll be dealing with the area of a sector. So the two formulas that you should be familiar with before are that the arc length is theta over 360 times 2 pi r. Now, I'm someone that doesn't memorize formulas, and I try to understand how the formulas work. So what this actually means is that, well, your sector has a specific theta that it comes from. So it's like taking a percentage. So if I'm doing 10% of $5, then what you're going to do is take, well, 10% is 10 over 100 of $5. So this is what you're going to do. You're taking a percentage of an amount. And this is what we're doing here. We're taking a degree of the 2 pi r, because the arc is part of the circumference, and the circumference is 2 pi r. So we're taking up a section of that circumference, which is the arc length. And how much is this section? Well, it's theta over 360. So this is how I understand the formula. So that's how much we're taking up. Now, to convert it to radians, what we're going to do is change the whole thing. So assume that we are now not dealing with 360. I'm going to replace this theta with an alpha so that we're not confused. So the alpha is your degrees, and let's say our theta is now the radians. So using the same concept, what we're doing is taking theta, this time whatever it is in radians, divided by our 360, which is 2 pi. So we've seen previously that 360 is equal to 2 pi, and that's in radians. So this is times 2 pi r, and we can actually simplify this. So this crosses out, and now I'm left with theta r. So how nice. The formula is actually simple. All you have to do, if you have a radian, for example, let's say the radian is 2.5, for example, and the radius is 3. All you have to do is take 2.5 times 3, and that would give you the arc length. So quite easy to do. And then we could do the same thing for the area of a sector. So the area of a sector is, the formula is, again, we do the same thing. We have alpha over 360, and we're taking a part of pi r squared. So the same thing, a percentage of an amount, but it's a degree of an amount. Not degree of an amount, but it's similar. So we're going to do the same thing and replace the alpha and the 360 with the radian calculation, and we're going to go theta over 2 pi times pi r squared, and again simplify the whole thing. This simplifies, so what we are left is 1 over 2, don't forget the 2 there, theta r squared. So this is the formula for the area of a sector. So these are the two new formulas that you'll have to use. This for the area of a sector, we're talking about sector here, and this is for the length of an arc, and the arc could be on, well, the arc has to be part of the sector because you're dealing with a theta. There are some sections where, some questions where you have a segment here So the arc is part of a segment and part of a sector, but in order to use this formula, you'll have to know the theta of this arc. So this is how it is. And in the first video for radians, I did mention that there's another proof, but it uses the arc length. So I'm just going to quickly do the proof. So we can use the proof for, we can actually use either. So let's just use the arc length formula. So the arc length formula is theta over 360 times 2 pi r. Well, we know for a fact that radians work for any circle. So it doesn't matter what radius the circle has, the definition of radians works for any circle. So we're going to take the most basic and fundamental circle in math, which is called the unit circle. And the unit circle has a radius of one unit. The radius is 1 unit. Centimeter, meter, unit, whatever it is. So now using the formula for the length of an arc, we know that let's assume we have the circle. Let's assume we have the radius of 1, and if I'm on 1 radian, then this length has to be 1. By definition, this arc is equal to the radius, and we're in a unit circle, so it has to be equal to 1. So it's 1 everywhere. So the length of this arc is 1. The degree is 1 radian. Let's just write 1 radian now. This is going to be a bit weird. Over 360. And the radius here is 1. So we have a nice equivalence here. So what we're going to do is simplify it. So we have 1 radian times 2 pi over 360. I know this looks weird because in the previous slide I was very picky about theta and alpha and so on. But because I've written radians here, it means I'm specifically kind of assuming a conversion here with the degrees. So it is correct as long as I'm writing radians. And then just to simplify it, I'm going to multiply 360 on both sides. So I'm going to get 360 here equals to 1 radians times 2 pi, which means that 360 is equal to 2 pi radians. So that's another proof of the equivalence. Might be a bit weird, but it's just another way of showing that it works.